the basic idea there is that the distribution of zeros of the zeta function and the distribution of the eigenvalues of some Hermitian matrix that's taken from a Gaussian unitary ensemble both obey the same statistics. That's the
yes, I remember that. Okay, but let's look for 1 second just for at Jose's idea. So is multi-wave function system, is it in the
yeah, it's in WFR. That's
okay.
Has been for a while, actually. It's criminally underused.
Well, it's a fine. It'll get used more if I get back to my multi-way systems based on numbers. Okay, so then this is function divisors of n. Does divisors of n produce the proper divisors? No, it does not. It needs to remove drop comma minus 1. Is that most? I'm always forgetting. It's not a function I use very much. Yes. Okay, so let's say we start with 100 and we go however many steps we need to go. Let's go 20 steps and let's go 10 steps just to be safe. And then let's say state scroll. Is that right? Oh, magnificent. Okay, let's see. Okay, so then the claim here is that if I were to just take, so let's say I take this, and what does the causal graph look like in this case? Well, let's say I take 1,000 here, and I say, that's rather jolly. Now, what happens when there's a transitive, does this need transitive reduction or not? Yes.
It have it, yeah.
It needs transitive reduction, otherwise it's going to do something crazy here. So
well,
you're
going to get dependency on the number of steps, amongst other things, which you don't want.
Okay, so that's the transitive reduction of that guy. Does that surprise you? No, 100 has those divisors. Those are the chains of divisors. So it is a grid at some level. Is that right? So how could I do that transitive reduction directly in the multi-way system? What I would have to do is to say that I want to go, what defines the divisors that go in one step here? Those are the things that are the largest things that divide it, right? 200 goes to...
The steps are the Yeah, interesting.
Okay, so let's try a bigger number. Let's try the famous 50-40 of Plato. Oh, a grid. Look at that guy.
Funky.
Why is this not rotating? Help. That's weird. I'm very confused by this. Oh, there we go. Well, that's odd, to put it mildly. So is this obvious?
We have our design for the Institute building.
Why? Those are the trusses.
Like that.
Yeah, we can have platonic trusses. What does this mean, actually? I mean, this diagram is probably some weird version of a voting diagram for a Plato Perfect Republic type thing. Because it's like people, what's that?
Yes, I see what you mean, but yeah.
In other words, people break into these sub whatevers. Okay, why are these grids? So each one, let me just understand something. If I were to make this transitive reduction thing.
By the way, because of the way you've structured the system, you never need to go more than 2 steps.
Because of the, why?
Because everything is going to map to zero. Everything's going to map to 1, right? 1 is always going to be part of the story.
Oh, because so I have to do the transitive reduction after.
Your terminal point is already populated after 1 step, so you only need to go 2.
Yeah, I see. Okay, but how do I unpack the transitive reduction on a single step basis?
I don't know. I'm trying to figure that out.
See, one thing that's curious is these things don't multiply together. Like 200 goes to 40 and 100. That's most curious. 20 goes to 4 and 10. Not a single divisor pair. I mean, not an actual. How do I count the number of layers here? Is it this longest path function?
I don't understand. All the paths have length 1. That was my point.
No, but in this case here, sorry.
Oh, sorry. Why is it longest path? Why isn't it just shortest path distance from the root?
All right, let's try it. But what I'm trying to do is relate that to prime pi. Boy, that's not going to be easy to relate. Total number of nodes in the graph is
Here's a fun one.
Oh.
If you look at the number of edges after 2 steps in the multi-way system compared to prime pi.
Okay, so let's look at that. The number of edges is just, let's see, why is the number of edges? What is the number of edges relationship with the number of edges? By the way, how do I count the number of edges? Do I just say edge count?
Yep.
What am I seeing here?
I don't know. My conjecture was the average growth rate in the edge count would be about the same as the average growth rate in prime pi.
Mm-hmm. That seems plausible.
But there's a lot of there's a lot of noise. It's hard to say.
Yes. But so prime pi, what happens if we accumulate prime pi? What is the accumulation of prime pi? I've forgotten. How does that work? Is it nth prime or something? In other words, if we accumulate, yeah, we're this is more like plotting Am I very confused? Is this like plotting? It's not prime of n, but what is this? What is this? What is this? Wait a minute. Which one is this?
I really
Which one?
Question.
What's that?
I completely don't understand the question. What are we talking about?
I'm talking about this thing here, right? That's the wiggly one, is the number of edges, right? And the number of edges is going to be maximized for round numbers that have lots of divisoring, right? And if I compare this with divisor sigma of 1 comma n, I think there, I'll get a different kind of, yeah, okay, let's try 0 comma n, which is that's just counting the number of, that's counting the number of edges, the number of nodes, right? That counts the number of nodes. Okay, what's the relationship between the number of edges and the number of nodes? They're clearly quite related, as we can see from these pictures, but each edge, oh, I'm not sure. But anyway, so the claim is right. So related to where was the math world version of this? Oh, anyway, all right. This wasn't the topic I was hoping to talk about, but what is the main conclusion from this? The main conclusion What is the conclusion? I'm not sure what the conclusion is, because this is saying, I mean, this n log n thing, what is that saying in terms of our sort of physicalization of the multi-way graph? Right, is it saying something? Imagine that this was a multi-way graph for a quantum system. What would this result tell us?
Well, it would be, I mean, obviously the kind of big picture conjectural idea is that there's a relationship between combinatorial properties of the multi-way system and the spectral properties of its associated Hamiltonian.
Right.
Which is an interesting idea that's worthy of investigation.
Well, and which we've already seen some version of in thinking about the harmonic oscillator.
Right, right.
Spectral properties of, quotes, Hamiltonian. And I think it's more like some kind of cycle structure or something. So in the case of the harmonic oscillator, what we believe is that the spectrum there is determined by the repetitions, literally in time, of the structure of the multi-way graph. Is that a fair statement?
Sure.
So what one might think for the spectrum here is that it is, curiously, look at that puppy. That is a very repetitive thing.
That looks like a proto-harmonic oscillator.
Yes. Right. Okay, so if we erase the state labels, I mean, only knowing that they're distinct, what do we conclude about this object? What is that object? That object is just a grid, right? It's just a two-dimensional grid, if I'm not mistaken. And this one here is essentially a decorated two-dimensional grid.
Right.
So the thing I was going to do here,
which is kind of obvious, that every vertex should have an in degree of, every vertex that isn't the root or the endpoint should have an in degree of 1 and an out degree of 2, because multiplication takes in two numbers and gives you 1.
That's not obvious to me. I mean, in other words, it's not obvious. Explain what the transitive reduction is doing on a step-by-step basis.
Yeah, we need to figure that out.
Right. You know what it's doing? It's one of them is always a factor of 2. If it's an even number, it's like the smallest prime. Are they the two smallest primes? 200 divided by 40. This is so pathetic. I think it's the two smallest primes.
What does that mean?
It means that the numbers you get, so what it means is that in this graph, I claim, well, what we're doing is we're taking the number, let's see, we want Okay, here we go. I think factor integer even has an option for this. Oh, okay. Take, which order are the factor integer numbers in? Yeah, okay. So first slash at take this comma 2, and it is then I claim that it is okay, so I claim it's going to be this.
What's going to be this? I still don't understand what is the question here.
Oh, the question is, okay, watch. This is my claim.
Okay, I'd like to know what it's claiming.
Well, what it's claiming is, what I'm trying to do is I'm trying to work out what the transitive reduction graph is, right? Without having to do transitive reduction, right? That was what I was trying to do.
Oh, no. Well, that part's easy, right? That's just the divisor function.
No, it's not just the divisor function. It's not, because each thing, okay, 200 goes to 140.
Right, because the divisor function is larger for 200 than it is for 40 by 1.
I don't understand that. I mean, what is it going to? So a number n has what successors in this graph?
All the numbers whose divisor function is strictly 1 less. Like what? Or strictly less, I should say. It's just a partial order by the divisor function. Wait, what's the issue here?
Okay.
I thought you
Which numbers are they? Okay, so let's write out what it actually is, right?
Yeah.
So
by what length of divisors of n, i.e. the divisor function.
okay, but if we want to actually compute what are those two numbers, what is it? Isn't it? Don't we take that first number and divide it by its two smallest prime factors? Because the set of numbers which are, look, the set of numbers that are smaller, that's how we get the transitive closure graph, is that the set of numbers that are smaller by their divisor function is that whole collection of numbers. 200 has many numbers that are smaller by it than it by the divisor function, by its divisor function, right?
But it's not the smallest ones. This is what I don't understand. It's all of them.
No, I understand. It's all the numbers that look. The light cone, the forward light cone of 200 is all numbers whose divisor function is whose sum of whose divisors is less than the sum of the divisors of 200. Is that true? No, that's not true.
No, the value of the divisor function. The transitive reduction graph is a partial order by the divisor function. Do we agree on that?
I think so. Yes, okay. But okay. So I want you to tell me a piece of code that computes the transitive reduction graph without going through the full graph.
Yeah, it divides by all prime factors of the previous node, not the smallest two. The way you get from one value of the divisor function to the next in the partial order is by dividing by all prime factors.
Okay.
Isn't it?
I don't think so, but okay, we can try that. Okay, hold on. This piece of code is somehow wrong. That's odd. That's correct.
You need to map divides over that. Don't you?
No, I've got the number 100 goes to 5020.
Yep,
right?
Okay, we're all good.
But I think the problem here is that if n is a prime, what happens when n is a prime here?
Well, nothing. You get
Oh, puff, 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 puff. It's not including 1. It's got to include 1. Well, let's try your version of this. It's got to include 1 in the case where it's a prime.
which it does.
No, it doesn't. Factor integer doesn't include 1. See?
Oh, wait, why does factor integer have to include 1? All that's going to happen is you're going to divide through by the number and you're going to get 1.
Yes, but you're...
Which is
okay,
what you want to get a self loop.
Oh, you're right. That only has 1 successor. Okay, so what the hell's going wrong with my code here?
I'm totally confused.
What?
I'm totally confused about what we're doing. I'm just going to write what I think is correct.
There we go. Okay, well, I just got the right answer here, I think.
Mm-hmm. Right, but if you try it on 30, you won't.
Hey.
As a minimal example.
Okay, and now let me do the other thing.
It's nothing to do with the smallest 2. It's just the divisor function. You're just dividing through by the prime factors.
Then why does it only have 2 successors here?
Because there are only 2 distinct prime factors.
But these are not prime factors. 200 times 500 is not equal to 1,000.
That's a complete non sequitur. Why is that relevant?
Oh, because you're dividing. I see. Am I very confused? I'm dividing through. You are probably correct here. You're basically saying that my. Hold on. I am simply confused, probably. Okay, so in this case.
If I take A over B and C over D.
Yeah, all right, okay. The basic mistake is that the take shouldn't be there.
Right. Yeah, it's just all the prime factors.
Yes. Okay, fine. All right, okay. Now I at least understand what's going on. Okay, so at every step, we're dividing each number by its prime factors, and that's giving us, So
in other words, the depth of the multi-way system will be determined by the exponent of the largest prime, by the largest exponent in the prime factorization.
Yes. So what this is saying is, okay, so let's say we were trying to do factoring, right? The difficulty of factoring is associated with what here? The difficulty of prime factorization. So prime factorization is trying to find the predecessors of 1 here. So if I take a product of 2 large primes, I'm simply going to get a picture which just shows that it's a very simple picture. Right? So if I say prime of 1,000 times prime of 1,001.
I'm not convinced that the difficulty of prime factorization has any meaningful interpretation in this.
No, I don't think it does. All
the factorization is done by the evolution function.
Yes, I agree with you. But in this case here, well, let's just do prime of 100 times prime of 101.
We'll find, I presume,
it's trivial.
Yeah.
It's trivial. Okay. So your claim, okay, so now if I were to do the corresponding plot for, I don't know whether I'm doing this transitive reduction thing, but if I were to do it for 2 to the n, there it is. Okay, so if I were to do 2 to the 7 times 3 to the 4, okay, so in general, this graph is some kind of straightforward product graph of each prime's thing. Is that right?
I think so.
It's a grid. Okay, so now,
I think multiplication in this case becomes like the analog of concatenation of string rules, or of a combining of string rules.
I see. So the presence of multiplication in the number is like the addition of rules to the multi-way system. It's like the concatenation of rules. Okay. Okay. But so now this connection with the Riemann hypothesis is something to do with the connection of this thing with prime pi somehow, or something like that.
Right.
Right? And so the claim is that this divisor function, that the sum of everything you get here is, yes, I mean, this is obviously the divisors, because what you're doing at every step you're dividing by, so it's not completely obvious to me what the number of edges is. The number of nodes is the number of divisors, obviously.
Right. I don't know what the number of edges is either.
Right, but this quantity that is being computed, this is saying, okay, the depth is the largest exponent, and the mass of this thing. So I mean, again, coming back to the connection with the zeta function and energy levels, what it means, if I'm not mistaken here, is, I mean, the infinite case of this would be some infinitely big number that's getting divided by, that's getting successive where you're computing successive divisors. And this thing will essentially show, if I'm not mistaken, this thing will basically be like a periodic thing for a long time, until eventually it isn't.
Right.
And the periodic thing that it is, so what we really want are the causal edges of this puppy. What on earth do they look like? So
take a look.
Yeah. I understand. All right, let me just get my function that does this one here. Okay, so all right, so let's go here. Evolution causal graph. Most curious. What the heck is that? The 3, what is that? What is that doing? What is that? 3 goes to 1 and then there's a 0? What the heck is that?
That's saying 30 goes to 10.
You can't be serious.
Well, this is what I get for cutting corners in the event rendering code.
All right, so that's a little bit of a bug, which should probably be fixed.
Right.
Okay. All right, so that's that one. So let's try looking at it for something a bit bigger. Oh dear, dear, dear. Incomprehensible. But what happens if I look at the instances? Then they should be, this thing is a causal invariant thing, right? So I should be able to look just at the instances of the causal graph instances. Should I not?
Yeah.
Okay, let's try a bigger number. What number would you like to try? Let's try a simple case. Let's try 2 to the 8. Okay, great. Now let's try 2 to the 8 times 3 to the 7. Ooh.
There's some interesting stuff going on in the instances.
All right, let's take a look at the instances.
Look at evolution causal graph structure instances, which is quite a mouthful. You may want to try it on a smaller number first.
And what do I learn from this?
So if you start looking at sort of 1,000, 2,000, that kind of area, you start to see weird repeats happening in the causal edges that I don't really understand, but may have some, the numbers that are connected by these kind of long distance causal edges may have some
Yes. Well, why don't we just see what those numbers are? Okay, if I take out the word structure, will I see?
Yep.
It'll be a huge mess. Okay.
It'll be a bit messy, but you can try it. I think this is one of the few cases where the aspect ratio of half might be making it less readable.
I think it will be even more squashed up if it's, okay, so then this is, where are the long distance edges? You're saying there's a long distance edge from 100, 200 down to 120.
And 120 to 10, 2. I don't know if we learn anything.
Oh, but because that's a, what on earth is that edge? What is that? What is that doing? What is the interpretation of the causal edges?
I don't have a good answer.
Let me think about that for a second. So the ordinary edges are dividing by divisors.
Yep.
The causal edges are connecting. The heck are they doing? Let's look back at an example. Let's look back at this example here. Well, let's see, we want this to be a layered causal graph. How do we do that? We just say in here, graph layout. Okay. All right. So now, why does 3015, why is that causally connected to 5,1? Help. What does it even mean? What does a causal connection mean here? I hope it's not doing it in terms of, I hope that this is not actually looking at the string characters here to determine causal connections.
No, it's not. It's, what was I doing? I had some scheme for doing this. Oh, that's right. I had a crazy scheme that you thought was silly.
Yeah.
But which actually is kind of a little bit tautological in this case. It was looking at the prime factors and treating those as the characters.
Oh, okay. Okay, so in the code, a causal connection is made between prime factor, between
Well,
shared prime factors.
but yeah, it's looking at creator and destroyer events of individual prime factors.
Right. All right, in any case, this is amusing. Yeah, so it may be somewhat tautological.
Right. I guess the real question here is, because the fact that this is connected to the Riemann hypothesis is kind of true by construction. The real question is, can we find a multi-way system in the wild that has the same structure?
Yes.
It was not set up to be number theoretic.
Well, I think the answer is yes. We've got plenty of grid-based multi-way systems. In other words, this structure of a multi-way system is something we could get with strings.
Right. But maybe this is a nice way to think about the whole Berry-Keating Hamiltonian idea, that it's just, the divisor function produces something that's analogous to the quantum harmonic oscillator.
Yes. Well, right. I think that's right. So let's think about that for a second. So the point is that at least for a while, I mean, the limit I don't understand, but at least for a while, what's being said here is, what is the period? I mean, literally, this thing is periodic with some period, if I'm not mistaken. Am I confused here? In other words, in the cosmological rest frame, yeah, there is a region here where this thing is purely periodic, right?
Right. With periodicity 1.
Indeed. Is it always 1?
I think it has to be, right?
Okay, so let's look here. Blow up the aspect ratio. I don't think that's, well, might be relevant. I don't know whether it's relevant or not. Let's say times 5 to the 6. Oh, and I don't really want to use this transitive reduction way of doing it. Oh boy, what is that creature? So,
yeah, maybe that's another thing worth noting, that the number of distinct prime factors basically gives you the dimension.
Yes. Okay, so this thing I don't understand what the dimension is doing relative to a harmonic oscillator, or
well,
yeah, go ahead.
I guess, if our way of thinking about the harmonic oscillator is right, then each prime factor is giving you is like an independent subsystem, right? Because each one is giving you a different branchial direction.
Yes.
So when you're taking a product of these distinct prime factors, it's literally a tensor product of one-dimensional Hilbert spaces.
Right, which is, it's an n-dimensional. So in other words, with n prime factors, it's an n-dimensional harmonic oscillator.
Right, exactly.
And so then the question is, what are the energy levels of the n-dimensional harmonic oscillator?
Right.
And what it's saying is, I see. And then, but what you're doing, what you're implicitly saying is, I'm going to combine an ensemble of harmonic oscillators, which is not something one usually does. But this is what we're doing. We're saying, let's take the energy levels of all. I'm a little bit confused by our hypothesis now. So if we look at an ensemble of different initial numbers here, we'll get an ensemble of different harmonic oscillators in different numbers of dimensions. Each will have certain energy levels.
Uh-huh.
And then what we're doing is we're merging those energy levels. We're just taking the union of those energy levels. And then we could ask questions about, if we take the union of those energy levels, do they, I mean, how does that relate to, for example, is the distribution of differences between energy levels, how does that relate to this random matrix thing and so on? In other words, go ahead, yeah.
Right. I'm wondering if we want to make the thing slightly more explicit, a more interesting multi-way function system we could produce is, so every time the zeta function changes sign in the, if you set the parameter, if you set the argument to be, 1/2 plus I times t, and you vary t, every time it changes sign, it has a phase jump of pi, right?
Yes, I mean, that's the Riemann-Siegel z versus theta function.
Right, right. So you could produce a multi-way function system of that. That would literally be an oscillator.
What are you proposing here? So you're proposing...
I'm saying evolve t in time, and what you get is something which the phase change of the zeta function is literally a branchial phase change if you encode it as a multi-way function system.
I am confused here. So you're saying Riemann-Siegel z. So if I take that function, if I plot that as a function of t, let's say t up to 100, t0 to 100, it'll have a bunch of sign changes. Okay, now what do I do?
Yeah, so I'm saying that we know that every time there is a sign change, there is also a phase jump.
In the theta function, I think.
Maybe.
No. A phase jump in what now? In the phase goes undefined when you're at a 0, right? And that's so if we were to look at z goes from, let's see, 0.4, that's half times I times t. So I times t is 0 to 0.6 plus 100i. So it's going to do the right thing. So I'm claiming that if this ever returns, oh God, let's just do 10. Oh, what are we seeing here? So that should be, oh, I see, that's the problem with that. Okay, so let's, so 10i plus 40i. Okay, so that claims to be the zeta function. I don't understand this now. So that's the zeta function in the complex plane near its critical line.
Yep.
So what I'm not seeing here, oh, because that's the absolute value. We need to do, wait a minute, how do I plot the absolute value? No, generates a plot of abs colored by arg. Oh, I'm confused here. If I were to plot, oh, I see, this would be a useful plot. Okay, hold on. a half plus I times t. Okay, this shows your, okay, let's say 30 here. Okay, so this shows the arg is changing discontinuously at every 0, right?
Right, and the jump is exactly pi each time.
Yeah, better be. Yep.
Right.
Okay, so now what's your point?
So my point is that's every time you have a multi-way function system and it evolves from one hypersurface to the next, you are incurring a jump in branch yield phase. Right.
Every time it evolves from one, well, it's, you can think of it that way, I guess. Yeah, go on.
So you could test, my point is only you could have a multi-way function system which produces branchings every time you get a phase jump.
Yes.
In the zeta function. And then you could just see directly, is the trace formula for that multi-way system the same as the trace formula for a one-dimensional harmonic oscillator?
Yes, that would be interesting. But it's not obvious to me how you get a multi-way system that has those jumps, right? You have to untangle. I don't see how you get that. See what I'm asking? I mean, anyway, look, can I return to a different topic? I think we should send this notebook to Jose and everybody.
But I'm just thinking that a multi-way system can where the states are real numbers can actually represent a complex function.
Okay, I had not figured this out. Okay, so I had started looking at ones where there's real numbers, but explain that.
But even if they're not real, even if they're integers, right?
Yeah.
You can have my point is that you can have so in other words, the integers are your space, but the branchial space.
That's interesting. That's a very interesting idea. That's a very interesting idea because that is relevant to our other project about the coordinatization of branchial space.
I know. It's actually something I used implicitly in my derivation there, but which.
All right. Okay. So hold on. So what this is
that was what I was saying about phase jump. The phase jump.
All right. Okay. So let's look at. Okay. So interpreting. Interpreting multi-way systems as having real and imaginary values. So what you're saying is that, oh boy, that's interesting. That's very interesting. Okay, so in other words,
kind of been using this all along, but
what's that? I know the coordination of branchial space is then the assignment of an imaginary part question mark. Actually, it's really a phase, right? It's then the assignment of a phase.
Right, exactly.
Which is what we've always claimed.
Right. Okay,
so then what you're saying is, so let's think about that for a second. Okay, so we think of the magnitude, again, we're just thinking of the magnitude as path weights and the phase. Okay, so now the question is, can we find a number theoretic function? Can we find a number theoretic example what does the, okay, what we want to do, let's take, for example, our divisor system here. Okay, wherever we had our convenient divisor system there. Okay, so now the question is there, let's take the case of 100, for example, here. Oh, boring. Let's take 400, for example. Okay, so now we should probably include path weights. How do I do that?
Include state path weights or state weights.
How do I get them displayed?
Vertex labels goes to vertex weight.
Why is that looking like it's labeling the edges, not the vertices? Or is it in fact labeling the vertices?
It's labeling the vertices, that's a layout thing.
Okay. Okay, so now the question is, in what sense can we coordinatize this with a phase going across this thing? So clearly, if we have a single, if we have, for example, let's say we have 2 to the 7 or something here, totally boring, right? So now let's consider the case 2 to the 7 times 3 to the 5. And now that's kind of created for us something okay, what on earth is the interpretation of those path weights?
Aren't they just, they're just multiplicities, aren't they?
Of those.
Of the, they're the multiplicity of that thing in the factorization of the things on the level above.
Right. Well, yes, I mean, that's true. So it's the exponent. You're saying it's the exponent. If I look at the prime factors.
So the fact that 864 has weight 3/8 is indicating if I take all the numbers on the previous layer and I factor them, 3/8 of the factors will be 864 or its factors.
Yeah, by the way, why doesn't this lead to 1 at the end?
It would if you ran it for more steps, I think.
Ah, good. Okay, so hold on. So you're saying, so for example, I claim, yes, look at that. 2 and 3, look at them down there. Their path weights are the exponents.
Yeah, exactly. They're the multiplicities of the factorization of the things on the layers above. Cool,
right. Okay, so path weights.
You want to know the other bizarre thing about this way of thinking about complex functions?
No, just a second. Let me write this line before I forget it. Are determined by the multiplicities of factors. So, e.g., the final primes are exponents. Final primes have weights that are their exponents in the factorization. Yeah, go ahead, sorry.
So the fact that the complex numbers are an algebraically closed field is a causal invariance statement, right? Because what you're saying is if you just have functions of real numbers, then you will in general produce multi-way systems. But once you have a multi-way system, there is a unique multi-way system.
You mean real integers? Wait a second. What do you...
Or it doesn't matter whether they're integers or arbitrary reals.
So wait a second. You're saying
if you have a single path. Right,
no, I get it. I'm just trying to clarify. Okay, so you're saying, okay, so causal invariance for Gaussian integers, which we're not doing here. Gaussian integers, I don't quite understand this. So you're saying if we were to, maybe we should look at Gaussian factorization, which we certainly could.
Right, okay, so fine, let's stick with Gaussian integers if that's easier to think about. So if you just have an ordinary, suppose you have a multi-way function system which just produces a single path.
Yes.
That's just a straightforward function on the integers.
Yes.
But the point is, those aren't representative of all possible functions. In general, those functions will produce multi-way systems that have multiple paths, and hence phases. And so you'll get Gaussian integers as opposed to just regular integers. But the point is that once you have the multi-way system, you're at your limit. You can't, how to say this?
Sorry, I'm being told in a little while I have to go, and my youngest child is having a COVID deformed early birthday party.
Oh wow! I didn't realize your birthdays were so close.
Well, no, hers is actually in October, but it's a COVID deformed because I think we're looking at I don't know what the statement is. It's probably something you could probably state it in terms of some bizarre foliation that's caused by some distance metric associated with people being separated by the COVID thing.
Right.
Okay. In any case, all right. Let me understand this Gaussian integers thing.
Right. So, but the point is, once you have a multi-way system, then that's your limit, right? There's no higher order object.
I'm sorry. I'm confused by this. Hold on one second. So let's go back. Okay, just a minute. So this is
okay. Let's try it again. So I define a multi-way function system over the integers.
Yes.
If I have the case where there's just a single path, then that's an ordinary function over the integers.
Ordinary what?
That's an ordinary function over the integers. An ordinary integer valued function. It would be a
being iterated.
Yes.
Okay, so hold on a second. So this is, we're considering real versus complex integer functions. Okay, so now I see where this is going. I just want to understand it more explicitly. Right. So what you're saying is, if I were to just take an iterated function, right? A straightforward iterated function. Let's say I'm just doing 2n plus 1 or some such other thing here. There's no variations here. It's just 2n plus 1, start with, let's say, 1, and go for 10 steps. Splat. What's going on here? Oh, I need to make that a list. Okay. This is a straightforward, this is a pure real function iterated iteration.
Right, and so you can think of this as being like the analog of an addition operation or a multiplication operation or some other operation that preserves algebraic closure over the integer.
Yes.
But the point is, we know that in general a multi-way function system will produce bifurcations. That's the more case. And so the point I'm making is maybe you can think of those as being like the square root operations that take you out of just considering integers.
I see. The multi-step, when it branches.
Yeah. So the statement that the reals are not an algebraically closed field is the statement that in general multi-way function systems.
Yes, I get it. When it branches, it's like e.g. solving for something, or taking a square root.
Right.
I mean, so in the case of divisors, for the divisor multi-way function, it's like solving for what divides, right?
Right. But then once you have the multi-way system, you have everything. You can't get any more multi-way than that.
What do you mean?
So as in, what if we now open ourselves up to considering not just single path multi-way function systems, but multi-way function systems, then it doesn't matter what the rules are. They will all be describable by multi-way function systems. And so that's the statement that the complex numbers are algebraically closed.
I'm not understanding that. First of all, remind me what it means to say the complex numbers are algebraically closed. It means you do an algebraic operation on a complex number, you get a complex number again.
Exactly.
Okay, but that's true of continuum complex numbers.
Yes, right.
I mean, if you do an algebraic operation on an algebraic number, you also get an algebraic number. And that's true for complex numbers too, right?
Mm-hmm. Yeah, right.
Okay, so how does that relate to this?
So what I'm saying is that we start from the single path multi-way systems do not populate the space of all possible multi-way rules.
No, for sure.
But the multi-path multi-way systems do.
Okay, so your claim, which is not obvious to me, claim any multi-way system this is a very bizarre claim, which does not seem obvious to me. Any multi-way system can be generated, any multi-way system graph can be generated from a complex function iteration. Is that what you're claiming?
Something like that. More just that you can think of complex function iterations as being multi-way systems, whether the converse direction.
Well, yes, I agree with that statement. So let's look at an example of that. I mean, if we just literally look at, I mean, this is, yes, I had looked at this actually, because I looked at it in connection with the whole Banat trees business. Right, so I mean, if I say here, this goes to, I don't know, n plus I times n plus 1, n over I minus 1, for example. And we start off with that. What's it going to look like? Oh, splat. Okay, let's forget about the state weights. Well, actually, we don't want to forget about the state weights. Let's go 5 steps here. 4 steps. Okay, let's make this a layered graph. Oh, what did I do wrong here? Graph layout, layer digraph. Okay. So there are a bunch of complex numbers. Slightly bizarre layering structure. So now what are you saying here? Are you saying that there's causal invariance here because of this algebraic field property? What's that?
I have no idea what we're talking about now.
Okay.
I have nothing to say about this example.
Okay. Is this example not what you're proposing?
I don't know what this example is. It's certainly not anything to do with what I was proposing, no.
Okay, well, look. This is a function. This is n goes to some.
I know what it's doing. I have no idea why it's relevant to anything.
Okay, well, then explain what you were talking about.
I was talking about treating multi-way function systems over real numbers as being interpreted as functions over complex numbers. Why that's in any way related to this, I'm not.
Okay. Well, explain. I don't get that. Okay, so I'm not understanding. So this is one of these.
You have the individual states, which for a real valued one would be real numbers.
Yes.
And you have the additional degree of freedom, which is the phase from which you can infer the complex, from which you can infer the imaginary part.
I'm confused. You're saying, I see. You're saying interpret. So if I take some function here, right? You're saying.
I'm not saying anything deep. I'm just saying phase is phase. I mean, we
Okay,
already
but
knew.
you're saying something like this. If I say this, for example, I say that 5 steps. Okay, and let's forget about the state weights. Okay, so this is your average sort of standard. So are you saying there's an interpretation of this where every number here is a complex number whose phase is somehow associated with its branchial location?
I'm saying that every hypersurface is a complex number. If you plot evolution graph, which is the actual thing we should be talking about. Actually, do evolution graph structure, because I'm not sure if evolution graph will work. Yeah.
Okay.
Right. So the point is, on each of those hypersurfaces, you have a collection of ordinary real numbers or ordinary integers.
Yes.
So one associated with a phase, which could be between I and minus I from one end of branch.
Sorry, you're saying that the position that the thing shows up in the graph is interpretable, that there's additional information, that there's the value of each function, the value of each number here, and there's also its position in, what are you saying here? You're talking about the fact that you could label these numbers with something that has a phase which is their position in branchial space. Is that the point? What is the point?
Well, yeah, it's what I said, yeah.
Okay, well, let's try to understand that. So you're saying that if we were to do that, we're trying to coordinatize this plot, right? In other words, each number, we're trying to, if we said vertex coordinates arrow whatever, we're trying to figure out. So do you claim that there is a version of this iteration such that the actual number put at each node is its coordinate position, or not?
No, why would that be the case?
I don't know. I'm still trying to understand what you're saying.
Okay, I mean, would it help if I shared screen? So,
yes,
you could just run the 2 times the hash, 2 times n, 3 times n rule. That'll make it.
Okay. Okay.
And say states graph, because I mean then we don't care about the evolution graph. It doesn't make a difference. And no, we actually view the states.
Okay.
Okay. So at the first bifurcation there, in the ordinary parameterization of branchial space that I developed, the 2 would have a phase of I and the 3 would have a phase of minus I.
Yep.
Right. But then if you go to the third state, the 4 would have a phase of I, 9 would have a phase of minus I, and 6 would have a phase of 1.
Yes.
And so on. And so the point is you can construct any arbitrary complex number that way. Each hypersurface can be treated as a complex number.
I don't understand your statement. The hypersurface can be treated as a complex number. I'm understanding that that as you mean each hypersurface is this slice here, right?
Yes.
So what are you saying? You're saying that as we go across the hypersurface, we multiply by some. What do you mean that the hypersurface is a complex number?
I mean what I just said.
I don't understand. Try again. Try a different way of saying.
4 times I plus 6 times 4 times I plus 6 times 1 plus 9 times minus I. That's a complex number.
Oh, I see. What is the significance of that number?
Well, it's the second value of that function after iteration.
Okay, so wait a minute. So you're saying.
Look, I'm not saying anything new. All I'm saying is that so we've been treating branch-like hypersurfaces as being superpositions of states with complex phases. All I'm saying is that works in the case where you don't have state vectors, but you actually have separate numbers.
Okay, all right. So the claim would be
It works in the scalar case as well as the vector case. That's all I'm saying.
Okay, hold on. So you're saying a quotes complete superposition of a particular space-like hypersurface.
It's not space-like.
Why not? It's branch-like hypersurface.
Because the space is the real number.
Yeah, all right, okay. Particular branch-like hypersurface. Can be thought of as a sum of the complex numbers obtained.
I'm just stating the superposition principle.
What's that?
I'm just stating the superposition principle, that's all.
Slow down. I think there's something more interesting here. Hold on. Still trying to understand. Some obtained, but so the complex numbers that you would get from the state weights, right? State weights, and here they're actual values, right? But you could also make up state weights here, right? You can have state weights for each of these nodes.
Sure.
Right?
Right. Yeah, complex numbers can have absolute values as well as arguments.
Right, from state weights and phases. Okay, so what you're saying is that we can think of this whole thing as a complex iteration, where what is that complex iteration? So the state weights here, how do I display the state weights? Just say include state weights. What's that?
Include state weights.
How do I display them? Vertex.
Vertex labels goes to vertex weight.
Oops, vertex weight. Is it singular?
Yep.
Okay, all right, great. So now what you're saying is, on each of these rows, I can make up a single complex number, which is essentially given by the minus I to I. We think of this whole thing as going around a circle, right?
Right. So like I say, I'm just stating the superposition principle. So in the ordinary quantum mechanical formulation of this, each state is an eigenstate. Each one is a state vector. And you're just summing those with the and the phases given by path weights and branchial coordinate. All I'm saying is that in this case, where each eigenstate is actually just a scalar, what you get post superposition is an arbitrary complex number.
I get it.
It's not. It's yeah. Like I say, it's not. It's not.
It's more interesting than you're making it sound like. Okay, because think about this. I mean, so remember, different quaffs will give you different complex numbers.
Mm-hmm.
And so in this grid here, where those are just binomial coefficients, right? Is that right? The weights here.
Yeah, probably.
Okay. So then what you're saying is, as we go across Pascal's triangle, we are assigning each number we're assigning each number a complex phase. So in other words, if we make table of binomial, and we can say binomial of t comma n, n goes from minus t to t, and let's divide that by 2 to the n, 2 to the t rather, t goes up to 5, for example. Okay. Oh, come on. What am I doing here? Oh. Yes. Okay. Why are there a bunch of zeros though? What am I doing wrong? Am I confused? Oh, I go from 0 to t.
That looks right.
Okay. All right, fine. Now you're saying that for each of these I assign a complex phase, and that complex phase is just n. It's given by the complex phase is n is e to the I 2 pi. Well, I want to go from minus what's it to plus what's it. So I want help me, 2 pi I over t times n over t, right? Is that right?
Something like that, yep.
Oh, silly. Okay. All right, so then this is, okay, so those are the complex phases. I don't know whether those are going to go from 0. What's that?
We may have an extra factor of 2.
In the complex phase.
We don't want it to loop all the way around, right?
Okay, fine. All right, so let's take that. Okay.
Yeah.
Okay, so now let's say total of that. Okay, so let's try taking what? What? Why are those all? Okay, hold on. Let's work this out here. So those numbers right now, let's see what happens if I say full simplify of this.
They're binomial coefficients, so they're symmetric, which means that all the real parts will cancel out.
I see. Well, that's your choice of. So what is that telling you? I mean, that is this case here, right?
Except it's not, because in this case you also have the actual scalar.
But this value here, but so, I don't understand the significance of that value. Because what we're asking for is what's this? What's that?
That is the eigenstate.
I understand that, but why do we care what the value of the? I mean, these are just labels for eigenstates, right? What we're looking at here.
Yeah. But you want an eigenstate at the end. Or you want a state at the end. You don't want an amplitude.
Okay, so which state?
You're summing disembodied amplitudes, which I don't really understand.
Well, there should be some unitarity fact about them, but there is, because we're just, if we sum the squares of,
oh, 1/16 minus 1/16 is obviously going to be 0, but 1/16 times 16 minus 1/16 times 81 is obviously not going to be 0.
Yeah, but I don't understand the significance of putting the actual values of these eigenstates into. I don't understand the significance of that, putting the value of the eigenstate into this computation, because that seems like a completely different thing. I mean, what you're trying to get, look, ultimately the goal here is to understand this coordinatization. Okay, the question is, you've got a layout here, and there is a distance in branch Hill space. And one question is, if you were to reinterpret this thing as some complex iteration, is distance in branch Hill space naturally associated with some, complex thing here? Did that make any sense?
Yeah, I agree. That's the whole point. Yeah.
Why don't you? Okay, so can you explain again why the actual state values should enter? What are the state values? What's the relationship? You're trying to make a complex function. I mean, you're just trying to invent some complex function.
I have no idea. I have no interpretation for what you're currently doing. When you take a linear combination of vectors, you don't sum the amplitudes and then multiply them and then say, oh, the vectors themselves don't actually matter.
But where's there a vector? What the value of the state? You're saying, I see. What you're claiming is what would normally be a state vector. You're saying it's just a number. What's that?
Yeah, in this case, happens to be a scalar, but we treat it the same.
So interpret that in the Hilbert space kind of way. So I mean, we could as well. What's that?
That is the interpretation.
Okay, but we could as well take each number here to be a little vector, right? A triple of numbers, for example.
Yes. And so again, okay. I don't understand what you're doing.
No, but I want to understand what you're doing, because you're saying that triple of numbers, we can think of that. How does, okay. In the ordinary view of sort of the Hilbert space, we're talking about each one of these states being off in some different direction in Hilbert space. But now, if we've got, if these are all scalars, well, let's say they're little vectors, triples or something, then we've got a very simplified Hilbert space, so to speak.
Right. We have some generalized notion of linear independence that's given by the points on the branch-like hypersurface.
Yes. I'm still a little bit, I'm a little bit muddled at how this all comes together, but I see the point. I mean, I think I see the point. So imagine.
I don't know. Yeah, I can try to write something up more formally, but.
Right. Okay. Just a minute. Imagine that every node has some small vector of integers, or just a single integer.
Right.
By the way, what are these numbers? Do you know what these numbers are in terms of binomial coefficients? The numbers that are in here? Is that obvious? I think I'd worked that out previously.
I don't understand. Aren't they just 2 to the n times 3 to the m for n plus m equals something?
Yes, they probably are. So those numbers, okay, so we can work out these numbers. Okay, so then each one of those is, for everything there, we're going to get, okay, so it is the list 2 to the, well, we're not quite sure what it is, 2 to the n, 3 to the t minus n or something.
I'm sure that's what else? Yeah.
Yeah, it's going to be something like this. Okay, let's look at this. 2, 3. Okay, let's see. Oh, yeah. Well, you claim this is nonsense, so I might as well remove this.
I'm not. I don't know what it was trying to do.
It was, okay, so hold on. So this is now, actually we want to divide this. No, these are the numbers. Okay, so we've got 3, 2, 9, 6, 4. 6, 4. Okay, looks fairly convincing. Okay, there it is. All right, so now,
you want to multiply
what's that?
You want to multiply through by the thing on %171.
Well, we might as well just put this as the phase there, right? This is going to be determined, this is going to be the phase.
Right.
Okay. So, and then this, then what we're saying is, wait a minute, is it e to the pi? Is that right, to multiply by that phase, the binomial coefficient?
Yeah.
Yes, yes. So we want to take, for each row, we now want to take the total So it's actually those two things multiplied together, right? Because that
First,
is,
first of hash, last of hash, and then do total over that. You want to multiply first and last within each sublist, and then total over the list.
which sublist? These sublists here.
Yeah. No. In each sublist of that list, you want to do first of hash times last of hash, and then total over the whole list.
But why don't you just put a multiplication sign in here? Isn't it just this then?
Yes, it is.
Okay. Okay. So now we say total slash at that. And now we say is that obvious? So in general, it's a multinomial function here. If we have two, if we were to have oops, actually what I want to do here is to say oh my God, the hell are those creatures?
That does look like a straight line.
Yeah, well, so it's probably just e to the, it's probably just some angle, which is probably given by 2/3 in the complex plane somehow.
Right. And that may have to do with the fact that it's one step one step convergent.
That it's a straight line.
Yeah.
Well, this is interesting.
Anyway, yeah, I think there's a cool thing to be figured out between the connection between foliations and branch cuts, and therefore of between hypersurfaces and Riemann surfaces, that will maybe allow us to get to use more technology from complex analysis to actually understand coordinatization.
Yes. And we have yet to figure out whether string systems are like string theory.
Right.
Because that might be related. I mean, if by the time we can represent, let me just think about this for a second. So,
because I mean,
yeah,
it's kind of not really an intuition I'd had before, but I guess it's basically right that a Riemann surface is like the analog of a hypersurface if you were foliating your complex, multi-valued function.
Yes. Let's ponder that for a second. Okay, so the claim is, okay, the analogy between Riemann surfaces and foliations is basically the question.
Or branch cuts and foliations.
Well, but what is the analog between choice of branch cuts and choice of foliations? AKA, I mean, so that would then mean that the Riemann surface, I mean, is closely related to, I mean, I don't know, it might be slightly dual to it, but something related to the,
Well, the point is each sheet in the Riemann surface is like a hypersurface.
Indeed. Right. That's very interesting. Do you understand enough about the whole string theory world to understand the relationship between Riemann surfaces and strings?
No, but I know some people who do. and
Why don't you ask some of them?
I will
mean,
ask.
Because very interesting. So I mean, because look, I mean, I was playing around with this continuum limited multi-way systems, right? And the question would be, what is the discrete thing that limits to these Riemann surfaces?
Right. And yeah, and you're right. I mean, if we solve that, then we automatically get the string world sheet.
Yes, I need to go. Okay. All right. See you later.
All right. Pass on happy birthday from me.
Okay. Thanks. Okay. Bye.